Now that we can actually calculate position with our receiver, we should probably talk a little bit about the accuracy of a receiver and mainly things that are going to influence that accuracy. The several factors are going to influence the accuracy of any receiver when it comes with GPS systems. The number one thing that's probably going to influence accuracy the most is the number of satellites we're able to lock in on. And we have to have a channel, and we consider receivers have so many channels. They might have 12, they might have 60, they might have hundreds of channels. And each one of those channels can lock into a particular signal, that PRN code, that carrier wave that we were talking about. And the more channels that we have, the greater our potential is for higher accuracies, because we can basically monitor multiple satellites at the same time, allow us to have satellites maybe fall below the horizon or go behind trees or buildings or other things that are blocking it, and allow us to maintain that accuracy. Of course, with anything like that, the more channels that we look at on a receiver, the higher that receiver is going to cost us. The number of satellites that are available at any given time while we're collecting data or using GPS to calculate position is going to vary. Some of that's going to vary based off of just the location we're at and what's visible. Because each of the satellites are passing around twice in a day, but slightly faster than that, that's going to shift how we see those satellites. And so tomorrow we aren't going to see them in the exact same position as we saw them the day before. And so it's important, especially if you're looking at something that really requires a lot of satellites available to be able to perform highly accurate calculations. Then to be able to get the most availability, a lot of times you're going to want to plan ahead. And there are some tools out there that are available to help with that planning process and allow you to determine what's available in the area that you're looking at collecting that data. And so you can kind of plan ahead and pick the time of day that's going to give you the best kind of configuration of satellites. The number of systems that your receiver is able to tap into. Nowadays, a lot of the systems, even the GPS chips that are in our phones, are going to be able to connect to multiple GNSS systems. And all these systems, we've talked about some of them previously when we initially talked about this video series and having the other country systems that are out there. Another system that we haven't really talked about is WAAS, or the Wide Area Augmentation System, which is supported by the FAA and the DOT for the U.S. That's a set of 3 geostationary satellites, which are satellites that remain in the same space in the sky that kind of cover the majority of the United States. They were originally intended there to help with air traffic navigation and allow navigation between airports and provide that for pilots and for aircraft. But it has been expanded after it's being brought to service to be used by a lot of different things, and the public has access to it now. And really it's a differential GPS, or a source of correction codes. It uses a set of towers across the U.S. that are basically collecting information on satellites and the errors, and it's uploading that correction value to these 3 satellites that are stationed above the U.S., and then those satellites are just transmitting those correction signals back down. So if you have a receiver that's WAAS enabled, which a lot of receivers are because it's a free service, then you can tap into that and get that correction signal to help increase your accuracy. There is a lot of other errors that are going on that in the system due to multiple things, and we'll talk about here in a little bit. But most of those errors we can help or try to minimize by using what we call differential GPS. And that's where WAAS was one of the things we talked about as a differential GPS. Essentially, the idea of differential GPS is that we have 2 units we're utilizing, one stationary and one's actually moving. We call the stationary unit the base, and we call the moving unit the rover. And the most basic type of differential GPS requires a tower or a base that's sitting there nearby or within a reasonable baseline from your rover, and it's basically calculating its position and its on a known position. And so it can know how far off it is and then relay that information some way, either through satellites like WASP or maybe through the internet or maybe through a LoRa type of radio system. And the method in which it does that and how close that base is to us and the process in which it calculates that are one of the things that we're going to be talking about when it comes to differential GPS. And the two kind of most accurate types are what we call real-time kinematic and post-processing. Real-time kinematic, we're actually calculating that error and we're broadcasting that to the rover, and the rover's making real-time adjustments. In a lot of cases, we may not care about that. RTK works really well when we need to make decisions on the fly. So in agriculture, we use RTK when we want to make sure we're navigating precisely. Maybe we're trying to drive directly over a drip tape system that we've put in place a long time ago. We want to make sure we're playing directly above that drip tape. And so we want to be able to navigate or control the steering on that tractor to put it exactly over top of that drip tape. If we're going out and surveying and collecting data points, we really don't care about what the values look like at the time of the survey, because we're going to input that data into some program and maybe use it for designing something. And so post-processing allows us to basically collect data with something that doesn't have quite the accuracy that we're looking for, and then compare that data to a base that's setting out somewhere nearby or in a system or network that's available, that's constantly collecting data at the exact same time that you're collecting data with your rover. So you don't always have to do it in real time. We can post-process it also. But the basis of any of these systems with differential GPS is that we have a stationary object and we have a moving object. And we might be broadcasting that information over. The other thing is we're going to have overlap. We need to have overlap in satellites so that a particular satellite maybe that's having some orbit irregularities, we're going to pick up on that and make those adjustments because the base knows exactly where it's at and how far away it should be from that satellite. And so having overlap in satellites is key to making this system work also. And that type of precision that we're going after, there's some terms that you're going to see on a lot of receivers and when you're looking at programs that are calculating this, and we call it DOPS, or dilution of precision. And there are multiple different ones out there. There are GDOP, PDOP, HDOP, VDOP, TDOP, all those types of ones. PDOP's the one you're probably going to see a lot because it's kind of a general term. It's a combination of a lot of the positional errors and the time errors that we see. And that's one you're going to see probably on a lot of receivers, or a lot of software is going to give you that value. The lower the value, the better. And so depending on what we're trying to do, we're going to have to choose a PDOP or a DOP value that's going to be low enough for what we're trying to do. But each of these kind of tries to describe things like the horizontal precision or quality. The geometric dilution of precision is going to tell us basically the position of the satellites. If we have the satellites spread out, they're going to give us a better GDOP than if we have all the satellites clustered in one little small area of the sky, because we don't have that spread. It's kind of, think of it as like a stool. If we have all the legs of the stool, if you're standing leaning on something that's basically one or two legs are really close to each other, you can wobble the stool around a lot. If you spread the legs out really wide, it makes it a lot harder to tilt and move the stool, because a little bit of change in the legs or the length of the legs isn't going to adjust your position that much. So DOPS are a way that we can basically measure some of these quality aspects of the solution that we're calculating. What are the errors that we run into? Well, there's a couple different ones. One's our intentional error. This is a kind of one that's not as prominent anymore, and that's what I'm talking about is selective availability. So selective availability was something that was incorporated into the initial Navstar system. It's essentially intentional error or muddying of the waters so that the calculation that you're getting is going to have some just inherent error in it. And so this particular graph I have here shows the error in meters for horizontal and vertical. Now you notice vertical is really bad compared to horizontal, and typically our vertical error on calculating position is going to be a lot higher in general than horizontal error. But the idea here is that essentially in May of 2000, President Clinton signed the bill to basically drop selective availability. And the idea was that we didn't want others be able to use our system that we've invested time into. And so if there were enemies of the state that were using this particular system, we could shut it out. Well, after 2000, really when the selective availability got cut off on those satellites, that was when we started seeing GPS getting incorporated into everything. And that's really kind of the kicked off GPS and the use of GPS in our everyday lives. Before that, we couldn't really tell if we were on the left or the right-hand side of the interstate or if we were off in another side road. So it made kind of all the little navigation systems that really flourished after that, give them something to do. So selective availability was just this intentional error built into the system. The modern satellites that we talked about in the space segment, a lot of those now are being built without this selective availability, even as an option. Satellite geometry, we talked about satellite geometry in the GDOP and the PDOP. The geometry has to do with how the satellites are being positioned. If they're all in one section of the sky, then that means that any small amount of error in one of them or a group of them can lead to a lot bigger position error. And so we tend to like our satellites to be spread out across the sky in different quadrants. And so we want to keep them like that instead of in a line or in a small cluster. And so it's something that we can't just directly measure, but it's something that'll help. It's going to basically help a lot of our other errors or augment a lot of those other errors if we're don't have good satellite geometry. Satellite orbits are something that we can't really control, but this is something that the control segment of this system works hard to try to minimize the orbit errors. And this is where the satellite's basically traveling at a position where it shouldn't be, or it's off from what it's saying that it should be at, or what it's broadcasting at. And a lot of this just has to do with the gravitational pulls and shifts in that orbit. And so the control segment is trying to continually monitor that. That's why all those new monitoring stations were added when we talked about in the control segment, so that we can continually monitor any of these little shifts. But they can shift up. All these orbit errors can really add up and be as high as 2 meters difference because of that. Multipath is one that we still deal with a lot today. This is basically where we get reflected signals. We normally think of, in this whole process, we've been thinking about a satellite and sending a signal straight to our receiver without going anywhere else. It goes straight to our receiver. The thing is, we don't have a satellite that's directly aimed at our receiver. It's not following our receiver around and constantly aiming its antenna. The antenna is not a narrow directional antenna. It's a broadcast type of antenna. And so those signals not only are going straight to our receiver, but there are a lot of objects that will reflect radio waves, and those objects are going to reflect radio waves right into our receiver also. And so multipath error, as the name sounds, we're going to have multiple paths in which the signal can get to our receiver. And usually new modern receivers are going to be able to handle multipath errors a lot better. And whenever we have a lot of things like really tall buildings around and things like that, things that can reflect our signals, that's where we get more of these multipath errors. Atmospheric errors, this is really influenced mainly by the ionosphere, which is the charged particle section of our atmosphere. And a lot of the signals or the satellite signals, they're going to get delayed as they go through that ionosphere. And the thing about it, it's not a nice even layer that has a consistent number of charged particles. It is just like our rest of our atmosphere. It's ever changing with the weather, and so there are patterns and changes. They're going to basically change how those radio waves, since our satellites are above that layer, get through that layer. And so there are a lot of programs out there where we can look at the forecasts as far as how that's affecting things. And there's also ways to avoid this error. And one of the ways we can do that is that using multiple frequencies like L1, L2, L5 are going to allow us to adjust for this ionosphere error. And some receivers are multi-frequency receivers, and each of those frequencies are going to be affected ever so slightly differently by the ionosphere. So we can help look at those effects between those different frequencies and be able to adjust. And dual frequency is the main way that we do this, and it allows us to calculate a correction based off of that. And then clock errors are basically based off of that synchronization between the clock and the receiver. We're probably not going to have a whole lot of clock errors. We can have some clock errors in the satellites themselves, but they tend to be pretty robust in that respect. Most of our errors are going to be based off the fact that our receiver doesn't have a precise clock. We're going to be using satellite clocks as a way to help update or correct those clock errors. And since we're using very precise measurements of time, and we've talked about previously when we looked at calculating the distance, a couple nanoseconds, a couple microseconds are going to make major differences in lengths that we're calculating as far as distances between us and the satellite that we're talking about. And so we can add a lot of error in just having our clock off by, microseconds or even 20, 30 nanoseconds. We're going to get a meter worth of error. So it's something that our receiver has to constantly be monitoring and updating and checking. And that's why we say we need 3 distances to be able to actually get a trilateration, but we want that 4th satellite in there as a way to just provide clock updates only.